Welcome to Chapter 10. This is 3 ways to make an alcohol. So Chapter 10 has been broken up. Really, so this is going to be review of the 2 ways that you saw in our Chapter 10 lecture, the previous one, and then this is going to include a new way to synthesize or make an alcohol. And the alcohol is made from an alkene. So this is an alkene to an alcohol functional group transformation. This is a review. The review of the other 2 ways, I will quickly go over those, so this will be a quicker video. We have an alkene starting material, and it's unsymmetrical, so these 2 carbons are not equally substituted. And so this is, we're going to add a hydrogen, and we're also going to add a chlorine across this double bond. So one of these is going to get the H, and the other carbon is going to get an H. This is Markovnikov's addition, Mark's addition. So we're going to do this stepwise, so we got to get the more stable carbocation intermediate. And this is electrophilic addition, EA, mechanism. And so the first thing that happens is this nucleophile goes and protonates the carbon. So we get this intermediate. And the hydrogen goes here. And on this carbon, we're going to get the positive carbocation. And then this carbon gets the hydrogen. This gives us a tertiary carbocation. And then we do the test, okay? If we switch places with the next door neighbor, that would be a secondary, that would be a secondary, that would be a secondary. So tertiary is the more stable carbocation. And now we have this nucleophile here that will come and attack the electrophile. And we've added the Cl there. So this is also hydrogenation, because we're adding a hydrogen, and a halogen across the carbon-carbon double bond. This is a tertiary alkyl halide, and so C is the answer there. Notice we have 6, 7, 8 carbons. We have 6, 7, 8 carbons. 6, 7, 8 carbons, 6, 7, 8, but this is the anti-mark, and we do not observe that product. So the answer is C. Okay, so I said that we're focusing on 3 ways to make an alcohol from an alkene. This is review. This is called hydration. And so we're adding water across the double bond using acid. Now what I do want to point out, so let's look at this bottom one here. Well, let's look at something like this. All right, so what would be, so if you added sulfuric acid and water, what would be the product? And what if you wanted, so let's say you wanted to make this product. Let's say you wanted to make this product here. Okay, let's say you wanted to make this product here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so we're going to call this product A, and we're going to call this product B. The question I have for you will, because we're going to talk about 3 ways to make an alcohol, starting from an alkene. So let's say we wanted to make this alcohol A, this alcohol B. Would this path make that alcohol? Well, let's see. So this gets protonated, because that's the first thing that's going to happen with the acid. You're going to protonate it, and that strong proton will protonate that carbon and give you the secondary carbocation. So you got to do the carbocation test. Do you see that if you switch places with this hydride here, you do a hydride shift, you get rearrangements. And you will always get rearrangements if you can get a more stable carbocation. So this hydrogen goes there, this hydrogen goes here. Now there's your carbocation, it's a tertiary, and now the water will come in and you get this, and then through a deprotonation, you get a tertiary alcohol. Okay, do you say that this is a primary alcohol and this is a secondary alcohol? So this pathway is a way to make an alcohol, but because you get carbocation rearrangement, this cannot make the alcohols A and B. So how would you make this alcohol? So this is your starting material. What reagents would you use to make B, and what reagents would you use to make A? From the previous slide, you would find that this is a Markovnikov addition. So the OH goes on to the more substituted carbon of the two. So this is more substituted than this carbon. So there's your OH. And you have no rearrangements. You'll find that you don't have a way to do that yet. That's what we're going to discuss, and this is going to be your new reaction. This one here is the anti-Markovnikov, and we did go over that. And if you remember, you do the BH3. Sometimes you might see that with THF, and then you use hydrogen peroxide and sodium hydroxide. And so, do you remember? So for B, let's erase this so we have some space to work here. So to do B, what's that mechanism? And you should know that from the previous lecture. Okay, so remember we said BH3. So the first compound you're going to make, the BH2 goes on the least substituted carbon, and the H is going to go here. And then the next thing that happens, and this is going to be either all dashes or all wedges, so this is anti-mark. This is also syn. Okay, so these the hydrogen and the BH2 added at the same side, and you can show that by all dashes or all wedges. And then the second reagent is the hydrogen peroxide and sodium hydroxide. This is an oxidation reaction, and we'll talk about that in the next chapter, chapter 12, really about oxidation reductions. But basically, for where you are at right now, you just replace the BH2 with an OH, and you retain the stereocenter, retention. So what does that mean? That means when you draw this product, there's your H and there's your OH. And so this is a way to make the anti-mark alcohol, the primary alcohol here. And like I said, this way with higher sulfuric acid and water will not make A, and that's why we're doing this discussion now. So mechanism of hydration, we've already gone through this, and you can review this on your own. One thing you need to know, you can also use methanol. So here, the first thing that always happens is you're going to protonate. So there's your protonation, and it adds the hydrogen on the least substituted carbon to give you your more substituted carbocation. This is a tertiary carbocation. It cannot rearrange because it would be less stable. Then the methanol can add, if you do this in methanol instead of water, and what you have then is this compound here, and then of course the HSO4 will deprotonate to regenerate your acid catalyst. Okay, so this is the new reaction, and this is really nice. Okay, so you also have a POGL exercise going through this oxymercuration. We're going to add oxygen and mercury, and then we're going to take off the mercury, and we'll replace the mercury with an H. So that's what D means, demercuration, to remove it. So we're going to add oxygen and mercury. Mercury is Hg, and we're going to add OH and Hg across the double-double bond. So one of the carbon will get the mercury, and another carbon is going to get the OH added. And that's what oxymercuration means. And then demercuration, we're going to remove the mercury and replace it with just a hydrogen. And this is going to give us a Markovnikov addition. And yeah, so it'll be Markovnikov addition without rearrangement. So if we have no rearrangement, that means we do not have no carbocation. So how does this work? Well, mercury acetate. So mercury is really like a 2+ here. So it's going to acetate is this compound here, and it's kind of more like a negative and a positive. It's a metal. So it's an ionic bond rather than a covalent bond. And actually that's not true. You can think of it like that, but mercury's kind of big. We'll make it a covalent bond. It's not one of those hard metals. Now, but mercury likes to bond two things, okay? So hopefully you can see that. And so this is the structure, and then it's in water. Mercury is a big fat proton. Big fat proton. Okay? Now, why is that important to know? It's because the mechanism is going to be very similar to what we just saw with acid. So what's going to happen is here you get mercury acetate, and then you get this intermediate, and you get mercury OAC, and it actually forms this three-membered ring, okay? So this is called the mercurium ion. Okay, so you saw this three-membered ring. You see just like the epoxides and like the bromonium. And then, but let's just actually, what if we had a molecule that was like this? Okay, so let's just take this. And the reason why we want it to be unsymmetrical, so let's take that. Okay, so if we had something like this, mercury, and now it's one OAC. See, it loses one of these OACs. Okay, and it does this three-membered ring. So we have a three-membered ring. And then whatever a nucleophile is, you have it in water. You can also have it in methanol. Now the nucleophile is going to add to the more substituted carbon. You see? That's the delta positive. It's kind of like a masked carbocation. But it's not a carbocation, so we don't have rearrangement. Now we have the ring opening. So what does that look like here? All right, so coming in from the top, you get this water, and you can just do OH. You don't have to do the deprotonation. And then you get the mercury OAC. And then the second step, number 2, is sodium borohydride. Borohydride is a hydride delivery. So what does sodium borohydride look like? This is the Lewis structure of that. You can do the formal charge for boron. Boron likes 3 bonds, 0 lone pairs. So this basically is a hydride deliverer, and it's going to replace this. This is a reduction. And we'll talk about oxidation reduction mechanisms in a couple chapters from here. But basically, this is the Markovnikov addition of the alcohol. All right, so they're just talking about mercury acetate. You're going to um, add this mercury acetate to one of the carbons, and you're going to make a three-membered ring, the mercurium ion, and it's going to follow McCartney's rule. So this is just your reagent here. Mercury is associated to two of these acetate ions, and they're kind of in equilibrium with this. Okay, so here you have the mercurium ion. It's a three-membered ring, and then the water is going to do a ring opening, and then you get deprotonation. So this is step one. So the first thing, when you do mercury acetate, and you add that in there, and you're going to do it in some kind of solvent. Here we're doing it water. So your solvent's going to be your nucleophile, and then that's going to open up this three-membered ring. The mercury is just kind of making this three-membered ring to protect um, the carbon from rearrangement. And then the nucleophile can come in, and then you get your organomercurial alcohol. And then the step, number two, is when you add the sodium borohydride. So this is the oxymercuration reaction. You're adding OH and you're adding the mercury. And then the sodium borohydride, this is the second step, and basically you just replace the mercury acetate with an H. Notice that this is showing you anti-addition because you're going to do the ring opening. And that might be important in your homework. And so they're showing you this mercurium ion, the three-membered ring, with the nucleophile coming in. Now we have an unsymmetrical alkene. So notice that the nucleophile is opening from the more substituted, that's that delta positive carbon, to open up that ring. And so that's how you get the Markovnikov product. And when you open up that ring, this puts the mercury acetate anti, and then sodium borohydride is going to replace the mercury acetate with the hydrogen. And it's going to maintain the anti. This won't matter so much because of the hydrogens. They're not symmetrical. They're achiral. So, I mean, that's obviously not achiral center. Let's see. So this is just showing you if you used an alcohol rather than water. So if you do this in alcohol medium rather than water, then the alcohol is going to be your nucleophile that opens up your mercurium ion. And in doing so, and then of course you deprotonate that, and then sodium borohydride will replace the mercury acetate with a hydrogen to give you an ether instead of an alcohol. And so this is just an example problem that you can get in your notes and an example mechanism. All right, so here we have mercury acetate and water. So what would that look like? Well, okay, so here's our carbon and our carbon, and you're going to get your mercury acetate, O acetate, three-membered ring. And so this is your three-membered ring that I would want to see. And then this is going to be your delta positive. So now water is going to come in. You want to make sure that that's not an alcohol. And then that's going to do a ring opening. So now we can show that ring opening. And so here we have OH here. We have that carbon there. And then we have mercury acetate. Make sure you got the right number of carbons. 1, 2, 3, 4. 1, 2, 3, 4. And then the second step is sodium borohydride. And that's just going to replace this mercury acetate with a hydride. So and we draw that in our notes. There's your OH here, and then you have that carbon here, and then this carbon got an H. So that's just going to be carbon. That is a tertiary alcohol. And there's your tertiary alcohol. Let's make sure we have enough carbons. 6, 7, 8, 9. 6, 7, 8, 9. So D is your answer. Now this is Markovnikov addition without rearrangements. What if you took this and you added sulfuric acid and water? You'd still get an alcohol, but let's show you why this oxymercuration reaction is such a beneficial reaction. Here, you protonate that, so you got to get a carbocation. So you're going to protonate, and you get a carbocation. That is a tertiary carbocation. However, next door is a benzylic. So you're going to get a hydride shift to get a benzylic. So that's going to go to the benzylic carbocation because that is actually more stable because of resonance. So now you got your carbocation there, and now your water will add here, and so it's still more Markovnikov addition because it's the more stable, but there's your OH. So this is a benzylic alcohol, 6, 7, 8, 9. This is a tertiary alcohol. So this would be that reaction if you use sulfuric acid and water, which we call that hydration. We do a hydration reaction. Okay, so I'm just going to quickly go through these because you have them. We've already gone through this, so you can go through this slide stack. But hydroboration, oxidation adds the H and the BH2 across the double bond. And then the second step is oxidation, which replaces the BH2 with OH. And this is going to be an anti-mark. And so here we have the H and the BH2 being added across the double bond, and then at step 1, step 2 is hydrogen peroxide replacing. This is an oxidation. That's why it's oxidation. Okay, you've already seen these slides. This is how you get the boron and the THF, and you make the alkyl borane. And this is showing you the mechanism that this is concerted. So the bonds are being made and broken at the same time. That's how you get syn addition. That means they're added on the same side. So I would like to see that all dashes are all wedges. And then you can derivatize in the lab. You can actually buy this boron with lots of different alkyl groups. And this kind of calms it down so it only deliver one hydrogen. This will be an important reagent in the next chapter when we're doing alkynes. Okay, because alkynes, we're going to do electrophilic addition of alkynes, and we will want an alkyl borane rather than the BH3 because the alkyne is more reactive. Okay, this is showing you an unsymmetrical alkene, and so if we add H and BH2, the BH2 is going to add to the least substituted. So it's going to be sterically driven, and this is the only product. This is not formed, and this is why you get an anti-mark addition, because then we're going to add hydrogen peroxide and sodium hydroxide solution. This gets replaced with an OH, and that's how you get the anti-mark, where the OH adds to the less hindered carbon. And some of it is electrostatic driven too, but I just think of more of it as a stick. Okay, this is showing you that the preferred product, the BH2, is adding to the less substituted carbon. Not happening. And then oxidation, you just replace this. Also, you get retention of configuration. So when you do the syn addition, you want to make sure that your OH is also maintaining. If you go with the wedge, you want to make sure it's going with the wedge. If you go with the dash, make sure it's still the dash. So you can add the hydrogen in one step. There's no rearrangements. The OH is going to go to less substituted carbon atom, so we call that the anti-Markovnikov addition. Syn occurs, so syn addition, that means you're going to have to do both dashes or both wedges. And the OH is going to maintain that stereochemistry. Okay, which reagents are not one of the three ways to convert alkenes to alcohols? And it would be this one. This one works, and this one works. You've seen these slides as well. This is just an example of installing your anti-Mark OH. Okay, fill in the missing reagent. So we have the phenyl here. And when you get the phenyl, you need to draw it out. We get this is the anti-Mark. So you want to see that. So this needs to react with the BH. This is going to be H and BH2. That's number one. And then number two, you replace it with the OH. So this gets replaced with the OH. So the answer is B. Here, it's asking for the product. So the other one we had to do the reactants. This one's the product. And so the first step, you want to take the time to put your H and your BH2 here, and then the hydrogen peroxide and sodium hydroxide would give you OH. So that's a primary alcohol. So you can see there's no alcohol there. That one's tertiary. This one's tertiary. This one's secondary. This is primary. And then count your carbons. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. A is your answer. Now these are just other slides that I'm not going to go through because, we went through this. So these are you. These are halogenation. You want to make sure you make your bridged halonium ion, and then it does anti-addition because it's going to be nucleophilic attack and open up the three-membered halonium ion. You don't get a carbocation. Okay, so you get this bridged halonium ion, and your nucleophile is going to come in from the bottom to open that, and will also come in from the top and open this. That's what it's showing you here. So you're going to get enantiomers. And if you have symmetry here, you've got to look for meso compounds. This is really nice to see if you do the Fisher projections, and the top and the bottom are the same. You can assign R and S and see that that is identical as well. Like when you're converting this is called a perspective drawing to a Fisher projection. Sometimes just drawing molecules differently and assigning names and classifications helps you problem solve, depending on what the question is. We don't use the calculators and the math to problem solve in organic chemistry, but sometimes we have to draw molecules differently, like the Newman projections, to answer the question. Halohydrin, this means you're making the bridged, and then the water will do the ring opening. And this is showing you that your halogen makes your halonium ion, which is a three-membered ring, and then the water is going to attack from the more substituted carbon to open that halonium ion, and you add an OH, which is hydrin, OH, and then you also add a halogen across the double bond. And here it won't matter because they're both symmetrical alkene. It is anti, but here they're unsymmetrical. So when you draw this bromine, bromonium, then you need to put your delta positive on the more substituted carbon for when the OH comes in. And you see that you get the OH is your only product where it adds to the more substituted carbon. And that's showing you the mechanism that we just did. And then so here you don't have rearrangements occur because you have the halonium ion. So hopefully you're catching on that this three-membered ring with the positive charge on the heteroatom keeps the carbocation from occurring, so you don't have rearrangement. And then the electrophile is going to be driven through this three-membered ring. And whenever you do that, you do get opening of that three-membered ring by anti-addition because it's a nucleophilic attack like an SN2. This is showing you, we've seen this in the previous lecture where this is added here and the OH is going to go to the more substituted carbon. All right, here we have, you got to look and see, you're adding OH to this carbon. So that's the more substituted carbon between the two. So we can say that this is mark addition. We're trying to figure out what reagents. And there's no rearrangement. So if you had a carbocation here, okay, so if you had a carbocation on that carbon, then you can say, well, that's secondary, but here this would be benzylic. So if you do a hydride shift to make the benzylic next door, that's going to be more stable. So did we get the OH on the benzylic? No. So this would be a rearrangement because we would go through the carbocation intermediate. So obviously we want to avoid that, so that can't be it. It's Markovnikov, so it can't be the anti-mark. HCl, what would that give you? I mean, you would get the carbocation rearrangement here, and then the chloride would come here. So that would be that product. So the answer is this one here. So let's just look. Your intermediate from your first reagent would be this mercury acetate, and then that would put this as a delta positive. The water would come in and open that, so you would get this here, which is the mercury here, and the OH here, and then this gets replaced with sodium borohydride. So the hydride replaces that to give you this product. So the answer is B. Here, what are we adding across this carbon-carbon double bond? We're adding a halogen and an OH. So this is the Halohydrin reaction, and it goes through this bromonium intermediate. 1, 2, 3, 4, 1, 2, 3, 4. So it's going to go through this intermediate. Notice I'm kind of working backwards. Okay, this is backwards. Retrosynthesis. So we got to go through that intermediate, so we need bromine to get there. So forward thinking, you need bromine, and then the OH comes from water. OH2 comes from water and opens that. So the second thing we add is water. So here, so you would use bromine and water basically. D is your answer. Um, so when you're trying to problem solve, you ask questions like nucleophile, electrophile, oxidizing, reducing, acid or bases. Okay, you need to practice this and work through problems. We did go through this, so you can, if you want an explanation on this slide, then go and look at the previous lecture. And same there. That wraps up this.